Okay. You have the pendulum activity, and to do the pendulum activity you need a washer and a piece of string. Now I'm not going to use the thin thread that I packed in your lab materials because it would be hard to see. So I've got a somewhat thicker string, and incidentally, if you've lost a thread, I'm sure the thread was there, but yeah, it'd be easy to overlook it and lose it. You can use any string, but make sure it's a thin string. Don't use anything this thick with the washer. It'll, it's got a little stiffness to it. Use something a little thinner, something flexible. Okay, so anyhow, we've got this, and of course the washer would be too small, so I've got this larger washer here. Okay, this is a large washer, and you might think it isn't a washer, but I guarantee that it is. Topologically, if this was a thin material, or sorry, not a thin material, but a flexible material, pliable material, we could squeeze and squish things around and enlarge this hole a little bit until we had a circular washer with a hole in it, without poking any holes or taking any holes out of it. Now I'm fudging a little bit because there's some holes through it here, but we'll pretend that that's all solid. Anyhow, so it's very simple. I tie the string around my washer, and I really don't have anything to support this. Yeah, I guess I can support it here. Excuse me a second. Okay, so tying the string around my washer. There we go. Now I want to, the instruction says lay the string out across a piece of paper. So what we're going to do is we're going to let this board here represent a piece of paper. Now your piece of paper would probably be, you probably want to orient it lengthwise. So let's say here's your piece of paper. Then we lay the washer out along the paper. Make sure you've at least got the hole over the paper. And we lay the washer out like so. And then we trace the washer. Okay, so we trace the washer. Here's the center of the hole. And on the washer you're using, center of the hole is the center of gravity, center of mass. And then we're going to mark a, well, we're not going to mark a point up here. We're just going to say that, okay, well, let's see now. I think I can, okay, I think if I tie a knot right about here, it'll fit onto the page. So let me just support this thing over here so I can use both hands to tie the knot. Okay, here we go. Let's bring that knot down here. We don't want it to be too long. Okay, there, I've got a knot. Okay, so here's a knot. And here's the washer. Now I'm going to line the washer up with where it was before, so I can mark where that knot is. Okay, mark it here. Now you want the distance, you want the length of this thing to be as great as possible while still fitting on your paper. So I was a little overcautious. I want to make sure it would fit on the paper, so it's a little lower than I'd like it, but I should be able to get around this. Okay, so now I grab this thing at the knot, just putting my fingernails on that knot, okay, so that the length of the thing is pretty much exactly where the knot is. And of course that's going to be a little easier to do with your thread, not as thick as this. Then I let this thing oscillate just gently, a few inches to each side. I hold it here and I count 1, 2, or I could count half cycles. The cycle is over, back, over and back. Okay? So I could actually count it 1, 2, 3, 4. That would be 2 cycles, but 4 counts. And you can figure out how to translate the number of counts to the number of cycles. That has the advantage that you're counting half cycles essentially, and that's going to give you better precision than counting whole cycles. Okay, there's no point trying to count anything less than that unless you get a rhythm going, like, okay, here's it. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. You can do that. But the main thing is to determine how many cycles this thing goes through in a minute. You observe that, and you observe it 3 times, and you write down your results. So I could write down my results, maybe even on the paper. Yeah, you might not be able to read that. I'm writing full length. Let's say it does 28.5 cycles in 1 minute. That's what it says. You write something like that down, you write your data on this paper. Incidentally, now, having marked the paper, you know how long the pendulum was, and you've got a record of how long it was. As opposed to, let's say, measuring it with a meter stick or whatever, and making an error on the meter stick. If you're careful and mark these things, you can mark this accurately, and you can measure it at will later. Okay? So anyhow, so we've got this documentation of what was done. Then I do it again. Then I count it again, and this time I count 29.5 cycles. And then I count it again, and it's still not the same. It's 28 cycles. That kind of thing is going to happen. Now, if you're a swimmer, I've always been a swimmer, counting laps, you learn to count accurately to, whatever number you need to count to. People aren't necessarily used to counting things accurately, and I notice that unless you pay close attention, in a class of students, college students, governor's school students, any class, counting for a minute. Maybe it's an attention span thing, I don't know. People aren't real good at doing that accurately, so make sure you are. I think everybody would be, but and of course some people are just inherently better at it than others. Different brains are wired differently, but try to get it right. Okay, well then I say, okay, well fold this thing over so that the knot is at the center of the washer, and line it up. And I can't do all that, this thing's a little bit heavy. And mark that position. And then count it. Okay, so I do those counts, and I get, half length, and I write my numbers. Got 3 observations. And then I fold that in half again and count it. And it's going to get kind of fast, which is why you want to have as much length as you can here when you start, because the faster it gets, the harder it gets to count. If it's too slow, you get bored. If it's too fast, it's hard to keep up. But you count it. That says quarter, and that's an incomprehensible word, but it stands for length. Quarter length, and you write down your observations there. Okay? And I haven't put it into the instruction, but I probably will. Now that I've got the video, or maybe I'm just going to recommend it through the video, take a picture of this and send it to me. Email it to me. Email me a picture of this page that gives you all your data. Now, I'm still going to ask you to report that because I want things in a format where I can insert comments and get it right back to you. And I want you to organize it on a page other than a handwritten page. But right here you would have a really good record of what you did. And if you copy it and send it to me, then later on when they try to give you a Nobel Prize for this and you've lost your copy, you can email me and I'll say, yeah, for $100,000 I'll send you the copy. Okay? Seriously, the idea of having multiple copies out there to back up your data is really a good idea, especially if you send it to somebody you can kind of trust to send it back to you. And you know, if you're really trying to back it up, send it to somebody younger because, you know, mortality comes along. Hopefully not too soon, but or send it to a variety of people so that it's well backed up. Okay? So there we have it. Then you're going to make a graph. Okay? And you know, you might even have room to do a small graph on the same paper. I don't necessarily recommend that, but it wouldn't hurt. But whether you do that on the paper or not, I want you to make a larger graph. Okay, a nice, accurate graph. But I'm going to draw it as if it's on the paper right now. So you're going to have okay, again, I don't know about legibility. It says y equals FREQ. FREQ stands for frequency. I'll go into more detail on and add some details to what we put in this graph. And then this is it says x equals LGT8 stands for length. You could spell out length. And you put your points on the graph. You're going to have 9 points. The lengths are going to be 1, now I'm kind of cramming this in. I hadn't planned to do this. This x isn't that x. This x is, you know, for the half length. But there's 1. Here's 1/2. And here's 1/4. That corresponds to the length of 1, 1/2, and 1/4. And then you're going to plot your observed frequencies. So my 28.5, my 29.5, and 28 would go with a length of 1. So that might be 3 points here. Okay, they won't be that far apart on the scale of the graph. But if you make a large graph, you're going to have 3 points. And you're going to get 3 points here, you're going to get 3 points here, then you're going to draw a curve that you think represents the function in a similar way to that you used for drawing the curve through your basic points of the squaring function to get your extended squaring function, which is the curve. Then I ask you to make some comparisons. Find parts of graphs of your 5 basic functions that seem to maybe have a shape that's the same or at least somewhat similar to the shape of this graph. And then we're going to expand on that. So there's a lot of profound implications to this exercise. Now you can't see my face. I'll get, no, where am I? Okay, here I am. Okay. And yeah, this lighting is kind of interesting here. I've got things lit there, but all the light is behind me. So that's an interesting phenomenon. Okay, well, the point is there are a lot of implications for this experiment. We'll be developing them.